Olá a todos. Estou muito feliz por estar aqui. Espero que a palestra entre tudo. E vamos começar. The rest will be in English, right? This is the... Okay. So we're going to talk about memory attacks, or attacks on memory, but with an additional constraint that the memory is encrypted. So, is the DRAM of a system really vulnerable? And maybe encryption would save the day. And by the end of the talk, we'll learn that the answer is no and no in both cases. So, we are going to discuss some demonstrations. All of them are very recent, and I would like to mention my collaborators. So, there is a paper that we presented at Host 2016 called Blinded Random Corruption Attacks, and this is a joint work with Rodrigo and myself. And another work, so this was around the middle of 2016. Later, there was another demonstration. It's called Fault Attacks on Encrypted General Purpose Compute Platform. And this has been published as a poster at CHESS. We just announced this, and this is with several collaborators, all of them from the Technical University of Berlin. So Jan, Jean-Pierre Seifert, and Julian Vetter, and myself. And you will see where we are going with this, and we are going to show something extremely new today, a demonstration by myself and Rodrigo. And this is going to actually be the first time that this is presented. No. Maybe this is better. So I'll start with background, some old news. So if you have an attacker, adversary in the crypto world who has a physical access to the platform, this is a big concern. And the two extremes are mobile devices like a cell phone that is stolen or lost, and there are many secrets residing in the memory. And the other extreme is the cloud computing environment, where the environment itself is untrusted, and who knows what's going there in the memory. So if you have secrets in your memory, you don't know who can read and access these secrets. And now, read and write memory capabilities as a hardware capability are well known and are also identified as an attack tool, and this has been demonstrated using different physical interfaces like Thunderbolt, FireWire. I guess that everyone here knows about all these. And the consequences of DRAM modification is that active attacks on the memory are possible, not only reading things, but also modifying. And if the memory is not encrypted, then the attacker can change code or data from any value to any chosen value. Because he can read and the memory is in the clear, he knows everything, and he can just bit flip anything he wants and change any pattern to any pattern. But this is too easy, right? This is known. So our assumption, our underlying assumption in the rest of this talk is that the threat model has an attacker with physical means to modify the DRAM. Now, whether or not this is possible or feasible or easy or cheap or expensive, this is beyond the scope here. This is our assumption. And let's see some different attack tactics. I'll put this banner. So a passive attack. So here there is an attacker only eavesdrops contents of the DRAM, but is not able to interfere with values or change them, and this is data in use. But this is not really an existent threat model. There are active attacks where the attacker can read the DRAM but cannot modify this when it is in use or to be used. And the classical example is the cold boot attack. So somebody gets access to your DRAM, maybe it's your phone or a mobile device, rips out the actual DRAM contents. Okay, you need to freeze it and to rush and plug it into another machine, and then you can just harvest all of the data, or most of the data. There is some degradation, but this attack cannot be repeated, right? You cannot rush back and plug it back to the machine. So it is a one-time attack, and this is an attack on the data privacy. So if you have something confidential on your device in the DRAM, then it is compromised. And the assumption here is that this device has disk encryption, because otherwise the attacker who wants to get your secrets will just rip out the disk itself and read. So the assumption is that somebody stole your device, it is in a locked position, and the disk is encrypted. So the only interface that he has with the system is just through reading the DRAM in this cold boot attack. And the last is active dynamic attacks. So here we have an attacker who can read and modify the DRAM contents while it is being used or before it is going to be used, and this is what we are more concerned with. Because typically if somebody has access with some of these tools, access to the DRAM, he can also modify it and not only read it. And now we'll talk about transparent memory encryption. So some technologies were proposed against dynamic attacks where the adversary can just read the contents of the DRAM. So first proposal is actually to limit the physical ability to read and write. Oh, let's block all the DMA access. But this is not always feasible or advisable, because these DMA access tools, they are there for positive reasons. You cannot just disable them. Even technically, it doesn't make sense. And the other proposal was memory encryption. So obviously memory encryption is a good tool to protect the privacy, but maybe there is more to it. So let's look at memory encryption using transparent encryption. And transparent encryption means that there is some filter that takes the data and encrypts it when it goes out to the DRAM and decrypts when it comes back. And this is simple. It is much simpler and cheaper than doing encryption and authentication. Because once you add authentication, you need to change the payload. So a cache line, when you write a cache line, you also need to produce some authentication tag in whatever manner, and then put it somewhere and get it back and compare the authentication tag. So this is much more expensive to do, not even to mention the performance hit that it incurs. And what it gives, the memory encryption changes the assumption on the read-write memory capabilities of the attacker. So the capabilities remain. This doesn't prevent the attacker from reading and writing, but at this point, the attacker who views values on the DRAM doesn't know what it is, because it is encrypted. And also, when he makes some changes on the DRAM, he has no control on what would be the outcome when this modified ciphertext is going to be decrypted and read back. So if the encryption scheme is valid and is good, this is going to create some random corruption in an unpredictable way. So there is some hope that maybe memory encryption, because of this limitation, is going also to be a good mitigation against active attackers, because the attacker doesn't know what he's changing, and it doesn't control what the outcome will be when it infiltrates the system. And this is exactly the opposite of the situation where somebody can modify the DRAM, an unencrypted DRAM data from anything to anything. So perhaps it is possible that encryption by itself is going to have protection. So the blinded random block corruption, this is the model that we want to put down when we are talking about active attacks on encrypted memory. So now the attacker has limited capabilities, and we call this BRBC, blinded random block corruption attacks. So blinded, the attacker doesn't know the plain text, so it is encrypted. And random block corruption means that the attacker cannot predict, cannot control the plain text value that would infiltrate the system if he changes something on the DRAM. So it's going to give some random corruption, and we point out block because the assumption is that if you make some memory encryption, if you prepare some memory encryption, you're going to at least have a block cipher, and it's going to be practically 16 bytes for each block. So at the very least, when you modify something in the DRAM, when it is going to be decrypted, 16 bytes of data are going to be completely garbled to something random. Oh, okay, random or unpredictable or pointless. So now the question is, can we rely on memory encryption to be a good enough mitigation in practice? Now, of course, there is no proof, right? If there is no authentication, there is no proof of anything here. But maybe it's good enough. Maybe it is so difficult to mount an attack on an encrypted piece of memory under these constraints that it is good enough. Okay, I think that you're guessing already where we're going to with the answer. So, a hint? No. Right? So what we are going to see that unless you are able to remove the underlying capabilities, if you are willing to block the DMA access or the physical capabilities, then you cannot depend on memory encryption by itself to give you the protection. Now, when you think about it, you would say, oh, of course it is obvious. Everyone who deals with cryptography knows that you cannot attribute more than privacy assumptions to an encryption scheme. But it is very tempting, since adding authentication to memory is very expensive, it is also very tempting to say, in a practical sense, this should work. The actual demonstration that it is possible to do such an attack and it violates this hopeful assumption, this is a surprise, and we're going to demonstrate several of them. So the BRBC attacker, blinded random block corruption attacker, is able to create time to check, time to use race conditions on the execution environment. He can change data, but in particularly, he can change the flow of any code, and if he's smart enough and knows what he's doing and has invested a lot of work into this, he can inflict real damage. And this is why we are here and what we're going to demonstrate. So first of all, let's talk about the model. We call this the ABC attacker. So there are several attackers with different goals. Right, so attacker A is an access-seeking attacker. So he's not an owner of a platform, but he got it to his possession in a locked state. So think of your laptop, you're sitting at Starbucks, suddenly you go to get another cup of coffee, you left your machine, it is locked, and somebody just steals it from you. So it is locked. Hopefully, you have disk encryption mounted, so otherwise the game over. So now the attacker has a locked screen. The only interface with the system that he has is the login screen, and the memory is encrypted. Oh, it seems like hopeless for the attacker. We'll see about that. Now, the B attacker, breaching attacker, he is a legitimate user of a platform. but he wishes to breach some of the policies to circumvent restrictions or escalate his privileges. So this is a much stronger adversary, because he has much more control on the system, and the most important thing, he can repeat his attacks as many times as he wishes. Because here, the A attacker is the weakest attacker, because if he does some modification on the DRAM and something fails, everything is going to crash, the system will reboot, and then the first thing that he's going to encounter is the disk encryption key, and he doesn't have it. So this is the weakest attacker, number A. B is a much stronger attacker. You can think of a corporate that with thousands of employees, everyone has a laptop, and everyone can access anyone else's laptop if he has the password. So, and one of the employees wants to read somebody else's mails. Okay, so this is the breaching attacker. And the conspirator attacker, this is a legitimate user and even has administrative powers. And he wants to actually collect information on other users' data. So if you think about this, this matches the situation of a cloud provider environment. You have some hypervisor. Let's assume that the environment is not malicious, but there is the night shift employee who is bored and he wants to read the memory of your virtual machine. So now this guy is also an administrator. He has everything. So we start from the weakest assumption on the adversary to the strongest assumption. And now we're going to describe, okay, well, I'm going to describe the A adversary. Okay, Starbucks stole your laptop, goes to his lab, and now he's trying to log into your machine. And we're going to describe this type of attack becoming a root on a locked system, right? You cannot expect more from an attack than to become a root on the device, right? So it so happens, or this is an attack on a Linux system, and the source code is of course open to everyone. You can just review this, and so in the code, I'm going to describe some of the flow. So there are some global variables, and there is a global pre-authentication flag, pre-auth flag, and the code logic runs as follows. If pre-authenticated is enabled, then you call the authentication mechanism, and if you are successful, you're going to be able to log in. And if not, then you are pre-authenticated to log in. So if you look at the flow, if you take the flow and make a BRBC, blinded random corruption attack on a block, and on a block that includes the piece of data that holds the pre-authentication flag, and maybe you're corrupting other things in the global variables, you don't care, then what's going to happen is that this binary decider, if it is pre-authenticated or not, is going to be flipped to something else, right? You cannot make a random corruption and expect that something would remain the same. So although you are corrupting much more and maybe other values, in this case you don't really care, because all you want is to circumvent a binary if statement. And then the authentication logic, if you change the pre-authentication flag, then the flow doesn't even, next time it doesn't even ask for the authentication logic. And you are already winning. So why is this happening? Exactly because you have a race condition between time to use and time to check. And in this case, the nice thing is that the process itself gives you an infinite amount of time to do your attack, because by definition it is going to prompt you the mechanism of the authentication, and it expects forever, if not forever, for long enough time. So this is just a wonderful example of a real program that you can just, you don't even need to do it quickly. You have a long pause, you go and drink the coffee from the Starbucks, and you go back and just do this random corruption, and you're never even asked again for the user password. So this is a case of a race condition that we can easily win in this situation. And now you would ask yourselves, does it really work? Can you really do this? Now remember that the assumption is that the adversary has the capabilities of overwriting the DRAM. And in some cases, for example, if you take Windows, the new versions of Windows, I think from 8.1, actually lock the DMA interface, the externally exposed DMA interfaces when the system is in locked position. Probably there was a reason for doing this, because in old systems it is not even blocked. But this is not a good enough mitigation, because if the attacker is really determined and wants to get your secrets, then he can just take the box and turn it out, and then connect to one of the internal DMA access connectors. So this type of mitigation is only a minor addition to the difficulty, but it is still not a real protection mechanism. And now I have an experiment. So we did an experiment, and we did two demonstrations. One of them is with a debugger. So this is like cheating, because if you have a debugger on the system, then you're cheating. But this is not really cheating, because what we could demonstrate was, so we used the debugger as the tool to overwrite memory. But the demonstration actually doesn't rely on reading the values, and it doesn't rely on whatever values are changed. So we just put something random. You will see what we mean. So this is just to demonstrate that the concept is correct, and if you really have these mechanism to read and write the memory, you can just win this game. The other one was with a JTAG device to actually to access the physical DRAM. Now the first one is something that everyone can do at home, because okay, just software, everyone has a debugger, you can just do this, you don't need tools. Here, if you really want to do this demonstration, you need to buy some piece of equipment. It is a few $1,000s, but you can still do this. You can also argue that if you have JTAG interface, then you can just do anything. But but again, it is just a demonstration for the fact that if you have the physical tools, then you can just win this game. So I'm going to show the BRBC attack on a login program with the debugger. But okay, so we are here on the attacked terminal. So you get a prompt for the login. Okay, we write root. We want root, if we could get this. And of course, what's going to happen? It's going to fail, right? We don't have the password. So now on the demo terminal, this is the demo terminal, this is a simulation of overwriting with some tool. So right now it's with the debugger. You connect to the login process, right? Here is an assumption that we know the address and we know where we are going to hit, but I'll discuss this later. Or you know what, on a locked position, when you are punching some erroneous password, the only thing that changes in the memory is something around this login program. So we know where we want to hit with our attack. The next, so in the attacked terminal, so just the attacker, us, just type any invalid password, and the login process then requests the username again, right? This is what happens. It'll ask you again and again, or at least a large amount of time before it does something else, because the legitimate user can be expected to make a mistake when typing maybe several times. So we have several attempts to do this. So of course, and here we just insert a breakpoint. And as you can see on the demo terminal, of course we cannot log in with this. And again on the demo terminal, so this is the overwriting. We just overwrite some random corruption. So we don't need to read, right? Because presumably the memory is encrypted. There is no point in reading what's there, and there is no point in trying to predict what's going to be the value that is decrypted with this thing. So we just put a random byte, a random 16-byte string. So 16 bytes garbage. If you count it, you will see that this is really 16 characters. So this is really 16 bytes. But you can do anything you want. And this is our random block value, and you can see this. So set the pre-authentication flag to 16 bytes garbage. So we just overwrite this with something that is arbitrary, and this is exactly a mental simulation of the situation we'll have if the memory was really encrypted. And then what happens? The next time, due to the random corruption, the pre-authentication flag was changed. Maybe something else was also changed. We don't care, but this just completely bypasses the prompt to enter the password, and voila, we got a root login. So what this means that even if the memory is encrypted, if you have the tools, you can just win this. So this is of course on the Linux, but because we did this on Linux because well, the code is open, everyone can see. But in other OSs, you can guess, you can analyze it. It cannot be a total secret to know how the login process works. Of course, the difficulty here is that you might crash the system. Like you might try something goes wrong, or maybe you didn't hit the right address, or for some reason the memory scheme is actually encrypting a whole 4 kilobyte page, and something really happens and the system crashes, and then, okay, then you're lost. But as long as you are careful, you have a good chance to do something like this. So here are the steps. So actually we had 6 steps that we ping pong between the attacked platform and the attacker's platform. The attacker is a debugger in this case, but it doesn't matter. Okay, so can we do this on a real device? And the answer is yes. I'll just show the picture. So here with the JTAG device, this was just an illustration to show that you can really go and modify blindly the contents of the DRAM. And okay, in our lab we do have the JTAG device. This is the blue box there. It is costly, but okay. So you cannot not go back home and try this, but you certainly can go and try the debugger demo, and it worked. Oh, of course it worked the same way that it works on the debugger. So what this means is that even for the weakest attacker with the smallest amount of control on the system and the smallest possible interface with the system, memory encryption does not guarantee the security. And if you can log in as root, then okay, then you don't, as an attacker, you don't need more than that. So in different attack scenarios, okay, we talked about the ABC. So if an attacker has more control, it is even easier. And the most important point is that in the B and the C attackers, they can repeat the attack. So there is no risk that something is going to be booted up and then you're stopped. Well, you can just repeat this as many times as you wish. Mitigations. I'm just going to touch this. Okay, so first of all, limit your DMA capabilities, at least the ones that are exposed. So this is already done in late Windows, not in Linux, but in late Windows platforms. But again, you cannot really do this because there are many interfaces, internal and external, and they are there for good reasons. So this is something that could be not practical. Software self-protection. So you think, okay, very well. Now that we know this trick, we'll go to the Linux kernel developments and tell them, listen, when you are doing this pre-authentication, maybe do a double check or do something in the code itself that would resist something like this. But if this demonstration happens on a real login, how do you know that you can possibly cover the whole kernel? I mean, you can do these things in many other places and change the behavior of software in an unpredictable way. So maybe you can patch here, but there are other places. So still it doesn't give you a guarantee that memory encryption is going to be enough. Okay, memory encryption with authentication is a solution. And actually, I just mentioned the SGX software guard extensions. This is a new technology, security technology by Intel, and this does many things, but part of it is that it has a memory encryption engine that has authentication and also replay prevention mechanism. It's not on the whole memory. Right now it's only on an aperture of 128 megabytes, but this gives you some chance of writing software that could not be attacked, because at least part of it is something that you can depend on as a root of trust and do something else. Now, I say there is more. I call it the revenge of the fault attacks. So fault attacks have been proliferating for years in the smart card world. Right, and there were many mitigations, and this is one of the most the easiest attack that you can mount on a smart card. And this is work with my colleagues in Berlin. And what we did was exactly the same thing. Assume that the memory, actually we built software-based memory encryption. Forget about the performance. It was not interesting. We just built it as a real demonstration. And again, we're assuming the adversary that doesn't have root privileges. So this corresponds to attacker B, the breach attacker. He can install malware or do many things, and in particular, he can physically access the platform and connect a FireWire device. This is actually what we are doing there. So you have a victim process here, an attack process, and the attacker there. I'm afraid to make one more step. So, and with a FireWire, he can control the memory. But since the memory is encrypted, the assumption is just that he can just override with something. And guess what? We just took the classical RSA CRT, so it's RSA with Chinese remainder theorem attack. It's classical. I think it's from the 90s. Bonnet, DeMillo, Lipton, they actually showed the first fault attack that it is based on some mathematical properties of the computations, but in a sense, if you can just corrupt a value during the computations, and these computations are long, right? So it opens a big window of opportunity to do something like this. If you just corrupt one of the primes, so the CRT is actually using the primes themselves in order to get some 4x speed up. So there is reason for playing with fire, but you can just, if you can somehow corrupt one of the values of the primes, then you can just factorize the modulus. If you see one good signature and one faulty signature, the greatest common divisor of the difference and the modulus is actually going to give you one of the primes. So your RSA is broken. So what is the mitigation that everyone knows that must be done? If you are using, okay, don't use CRT, right? But nobody wants to give a 4x performance on signatures. The other thing is, when you are producing a signature, before you release the signature, just check that it verifies, okay? So check before releasing a signature. Of course, there are papers, demonstrations, advice, BKMs, but still not everyone follows this. So guess what? I'll just jump for the sake of brevity. So first of all, we found a real piece of code. It's called GNU-GP, which is the mail client of many systems. But I just want you to relax. It was an old version of GNU-GP, version 1. Version 2 already learned the lesson and is checking and also doesn't allow the interface through a script. So you cannot do something like this. But a real product, GNU-GP, actually, we can just do the same thing. So, okay, the attack actually consists of several steps, and each one of them takes a lot of effort to actually do it. So you need, first of all, on the system, you need to identify where exactly your key element P, which is the prime, where it resides. So first of all, the code is known, but you need to know where to start with. You need to know the offset. So you need to do some prime and probe work in order to identify where. So this is the preparation. The pre-phase, of course, you need to set up the DMA communication and to do some profiling in order to know when and where, and then you just do the attack. So the attack is through the prime and probe against some garbage corruption on the DRAM, which just injects garbage in this piece of data structure where the prime is located. Now here in this case the prime is large. It is 1024 bits, so corrupting 16 bytes is not even going to go beyond the boundary, and also we don't care. All we need is that it would be a wrong value of this prime. You do the faulty injection and you get the faulty signature, and you can just factorize the modulus, and which this means that you broke the RSA signature of this mail client. Without getting into too many details, I just want to tell you that we were trying this and we got 60% success probability per session, right? So it is quite probable that within a few attempts like this, you will get this done, right? And in this situation, if it fails in the first time, you just try it the next time, because it is a script that GNU-GP is willing to, it's like a command line script that the GNU-GP happens to accept and just produce the signatures. So the important point is that here we have a very high probability of succeeding even in the first time, and in a situation where we can repeat this several times, well, in 5 times you already get something like 90% or even more. All right, now, so we touched the A attacker, the B attacker. What about the C attacker? And I would say that the C attacker is actually the most worrying, because everyone today goes to a cloud provider. They're like Amazon Web Services. You buy or you get a VM, you run things. How do you know what's happening in this environment? Who is reading or accessing this VM's memory? So there are new techniques that have been released, I think, a few months ago by some processor vendors, where they have memory encryption and more. Each VM would have its own encryption key. So now if you are the administrator and you own the hypervisor and you try to access the memory of another VM to read it, so today if it's not encrypted, the hypervisor can just access and read the plain text. But now if it is encrypted and every VM has a different key, then even if you are an administrator of the hypervisor, unless you corrupt the hypervisor, but let's assume that the hypervisor is trusted, then you can read, you can access, but the ciphertext of the VM memory is going to be decrypted with a different key. So what you're going to get is garbage. You're not going to get anything. So I think you can guess what's coming next. All right? So I'm going to show a virtualization-based BR, blinded random corruption attacks. And we'll show you step by step, and then I'll call up Rodrigo. Where are you? Be ready? And we are going to make a live demo of this with some new twist. So let me show. So again, we have an untrusted environment, and you want to protect the privacy. So each customer today, just the administrator can read anything, and this is not an acceptable situation. And there is a new technology that says, okay, let's encrypt all the memory in this environment, but each VM is going to somehow get a different encryption key, and we are protecting. So protecting all the privacy of all the customers. So how about this? The ad. Your data privacy is safe with us. Your VM memory is encrypted, a unique per VM encryption key. So let's log in as root to your VM, okay? And you can now recall what we did with the locked machine, and you can imagine now that we are in even a better situation, provided, okay, that we do the right legwork. And we're going to demonstrate this. So did you know that there is a file, a config file for each VM that allows the administration to enable debug? Okay. And this is a very important feature in VMware and most hypervisors, right? Because you want to debug things when things don't work. All right, so you just can go as an administrator. We are now administrators. We can work with the hypervisor, but the hypervisor is trusted, so we cannot modify, right? The assumption that it was measured and trusted. So, okay, you can just put true in the config file, so now we can debug. But this still is not going to help us, right? Because debug means that we can just get it to read something, but when we read it, it's going to be decrypted with the wrong key and we get garbage. Okay, no worries. But, so did you know that this feature also grants us the ability to write the memory? And this is exactly the tool that we were looking for. So combine this in the scenario, you can just, okay, and did you know, okay, there is another thing, did you know? Okay, so the user actually connects to his VM through a connection, through a secure connection. But did you know that in the background there is also the login process running? It is not exposed to the user. It is not going to be used to the user who is going to do some SSH session with his own VM, but it is there running. Okay, now 1 + 2 + 3, and you can guess what's going to happen now. And here it is. So we connect to the hypervisor debugs tab. You can just see. So we have an attacker VM and an attacked VM. So the attacker is the hypervisor. And okay, so we connected to the target remote VM that is running. This is our victim. Now we are connected. You can see below, and we have now, as the admin, we have control on the execution of the target VM. You can just put breakpoints because we are able to debug. So the show must go on, right? We just connected to this, but we just hit the C. Continue, and you continue. The attacked VM is going on, and meanwhile on the targeted VM, what's happening? The VM boots normally. It is asking for the key. Enter your passphrase, right? And the funny thing is that the legitimate user has no way to know that the VM is being debugged. From his viewpoint, it just sees a normal screen doing whatever he wants, but this is going underneath. So guess what? We don't know the pattern, right? We want to be root, of course. If we can do something, if we can get root, then we will be root. We just punch some password. We don't care what it is, and of course it is going to say that login is incorrect and go back to the login. And all we need to do is the same trick as before, just to corrupt the pre-authentication flag. So, okay, please stop. We can control the execution flow here of the victim virtual machine. So Control C. Okay, we just stop this process, and you see it below. And now we add a breakpoint through the debugger, and this is a legitimate interface. That is a nice service to debug things. So this is there for a reason. A breakpoint. Let's see if we can try this again. You will see, first of all, that we try to log in, and now the VM hits the breakpoint. Okay, we put the breakpoint there. And if we try to log in as root without doing the corruption attack, of course we are going to fail. Again, it's the same thing. Give you your password, the password is incorrect, I'll do this again and again. But if we do the random corruption in the same, okay, wait a second. We have, so where is, we tried, we won, no, it was, so, okay, we say we're going to use the number pi to help us. So why pi? Because it is like every time, at least in the cryptographer's world, every time you want to put some random value or arbitrary value, you use the first whatever digits of pi written in hexadecimal or things. So pi stands for something random or arbitrary. So we'll use the digits of pi. Why digits and not the login process is expecting digits and not characters. Okay, so pi is a wonderful thing. So first of all, here are the real digits of pi. And we took the first 9. Okay, you can take as many as you wish. And here it is. We did the random corruption by overwriting the memory with the debugger. Now the debugger is a real attack. It's not a mock attack. It is. We just at the breakpoint we just set this value to be okay. You can check. This is the real numbers of pi. It doesn't really matter. And we won. We got root into this VM. So what this means is that memory encryption, even if you have a per VM unique key, is still not enough, because just encryption cannot protect you from random modifications that would infiltrate the system if you are fiddling with the values of the DRAM. And now, since this is a hackers conference, I know that you don't believe any of these things, and we're going to invite Rodrigo and make a real demo, a live demo with the two VMs, exactly this. But we are going. No, give me that this just for a minute. Yeah, but we're going to have a twist. So here is the twist. So today is my birthday. Happy birthday to me. And the date is October 22nd. And instead of pi, we are going to use this birthday attack. And we'll put 22nd of October, and you'll see this going live. And then you will believe it, right? So it has really nothing to do with the value pi. You can just put anything you want. Okay, go ahead.
Hello. So it's very weird to speak in English to Brazilians, but I will try, okay? So first of all, we have two VMs, right? We have the Red Hat VM, which is the attacker, and we have a Debian VM, which is the victim. There is no reasons for choosing one distro over the other. It's just like random distros. The idea is really to show that we don't need to know much about the victim. So in the configuration file of the victim, as Shay has explained before, I basically just enable debug. That's it, right? The victim don't know it's happening. So when I start it, it's actually stops the execution in a black screen, so you will see it in a minute. You see, the execution just don't proceed. It's waiting for someone to connect a debugger into it. That's just a capability that VMware gives to us, right? So we connect to that debugger. As Intel employees, we're doing marketing from McAfee right now. So as you can see, McAfee indeed works, blocks the connections, very secure. You see, live like marketing. So sorry, so I will try again. Okay, that's interesting. Let me just confirm again. Yeah, it didn't work. I will need some minutes, so I'm sorry.
It's a attack.
It shows it's really live, right?
We thought to make a video and show it, but we took a higher risk, right? So bear with us for a minute. You know, everyone can prepare a video, but to do this live. Okay.
Okay, now it's working. Yeah. Okay, so I'm back, sorry. So what happened is like I was connected to the VPN, sorry for that. So here we go, and it's another product and marketing, okay? The VPN is Cisco, by the way, it also works. So okay, now I will try again. As you can see, as soon as I connect to the target, if you look, the machine seems to be running. It shows like, if you see like here in the up corner here, it shows the machine is running, but because it hit a breakpoint as soon as I connect, it's just stopped. So I just hit a continue, you see the VM starts booting. Cool, so the user don't know, right? Imagine like now he's looking to his console, his interface from the cloud provider, he's installing his machine, he has disk encryption, he puts some password. The machine boots, he's using his machine. You see it's very, very fast because the interface is to the hypervisor. So it's really fast, like unless you really tell that you want to do something, the user don't have any perception of what is going on. So basically, if I hit a Control-C and I come back to the attacker machine, you can see it paused. You see, like the machine is waiting. So the debugger is really controlling it. So here we can set breakpoints. So for example, I put a breakpoint in a place in memory. And actually, that's one of the ways for you to know where is the program you're trying to target. You can put random breakpoints around and see when it hits. So there is no way you don't win. You find the program in memory, right? So I will let the program continue. You will see that when I type root, the machine pauses again because it hit my breakpoint. Now, we basically do the corruption.
Do you remember the number?
I hope. Let me just confirm, just to not crash it. Oh, you see? So 0. Okay, yeah. So we just do the corruption.
2nd of October 2016.
We continue the execution. And, oops, it failed. Let me do again. Hit the breakpoint again. The debug stop crashed. Shit. Well, I crashed. Sorry. I will need to restart everything again.
Okay, anyway, while this is going, and we hope to see ourselves as root, just watch here that this is exactly the situation of an employee or somebody who is working at the facility of the cloud provider, the assumption is that he cannot change the behavior of the hypervisor because the hypervisor is measured, so it is trusted. But he can certainly do all these things, and the user doesn't see or is not aware that this thing is happening. All he would see is that sometimes his VM is going to boot again, so okay, or he sees some delays, but this is considered to be normal execution, right? You can expect things like this, and even you can expect things like this to be routinely maintained as part of the maintenance of the system. So actually, this attacker can also target the timing of his attacks to those times where a boot is expected. So this type of attack can be done anytime. It is invisible to the victim, and also can be repeated, as we can see, can be repeated many times until it succeeds. By the way, it doesn't always succeed, right? As we said, we have some probability to succeed, but after some times, with some wishful thinking, it should work, and we will see ourselves as root. Okay.
Yeah, okay, so it hit the breakpoint again, okay? Just like to show that we every time we try to log in, we will hit that same breakpoint. So I will just let it continue. The login fails, right? Without corruption, you don't log in. So I will just make sure that I will try to type a little bit faster, just because the login process itself has a timeout. If it times out, it will get a different memory location. So obviously, if I corrupt, I will do something wrong. So that's why probably it failed. But let's try again. So. Yeah, the stub is quite. Hitting the brake. Okay. Here we go. Yeah, it failed again. Sorry. Okay, give me a minute. Let me make sure it works, and I come back.
Okay, we'll try this, and then I could. Okay, so I will just meanwhile say the closing words. On this. I hope that this talk convinced you that just encryption of the memory is not a dependable, at the very least, to say, not something which is a dependable protection against attackers, and it is really alarming that some vendors of CPUs actually are proposing this type of encryption as a mitigation or privacy mitigation for the cloud environment, under the assumption that privacy is protected through a per VM key, which is correct if we are looking only at the privacy, but at the same time you cannot neglect the threat by an active attacker who can just do such corruptions well, I hope we'll see, at a high probability of success. And the conclusion is that if you really want robust mitigation, you need to do encryption with authentication and pay the cost of the performance and hardware cost, or everything that it costs in order to really provide robust protection. Plus, I would even say that even just static authentication is probably not enough. We haven't targeted this, but once you have encryption and authentication, the next step would be to do a replay. Right? And you can imagine that you can possibly find a target and do a replay attack with the same technology, do a replay. So the only thing that is really robust is encryption and authentication and replay protection. And today, the only technology that actually has this in a CPU as part of the hardware is the latest processors by Intel that are supporting the SGX technology, and part of the memory is indeed encrypted, authenticated, and replay protected with all the cost. I mean, it is very complex to actually do this. You need to build some tree, some hierarchy tree in the memory in order to protect this, because the amount of internal SRAM that you can invest to hold some state for the replay protection is limited. So you need to use some techniques, some compression techniques, and they cost something like, on average, something like, I would say, 10% on those applications. But this is what can be considered as a real guarantee that you have protection on your information, whether it is direct privacy or indirect corruption attacks. So, okay. I think yes, we can just steal a few minutes in the next. We owe you this. Maybe my birthday doesn't work and we need to do pie. You think so? Okay. Okay. So we will show it later, right? And okay. So I thank you very much for attending, and I hope that it entertained you. Questions? Yes. Okay. Please go. How is it helping? Okay. So let's say that the question was how authentication would help this situation. So here what we were doing was to take ciphertext and modify it, and then what infiltrates the system is some garbage, because something is being decrypted, the wrong thing is being decrypted with the wrong key. But if you have also authentication, then if you change something in the DRAM, while it is being read back, it is not going to, the authentication tag is not going to check, and then it will just, okay, then it depends on what you decide to do. You can just kill the VM or boot the whole system. For example, in the SGX machine, if some corruption is or if there is a MAC mismatch on the authentication tag, it is just going to boot the system. So you will never be able to have your corruption or wrong information go into the system. And this is what makes it even more expensive. On top of the hardware and the space in the DRAM that you need, you also need some way to communicate that a bit that says something went wrong with the authentication, and make some policy, apply some policy that would stop the system. All right, last question, okay, please. Last two questions.
How would ASLR... Só um minutinho, precisa de microfone, Miguel. Okay. A menina não ouve lá. In an encrypted memory situation, if you had ASLR and KSLR, how would that prevent the breakpoint from being set at a known address to do the time to check, time to use?
Okay, it will only make the life of the attacker more difficult, but it could also be circumvented. You can imagine that this is not a robust, it cannot be a robust protection. It may lower the success probability or make the effort more difficult, but you cannot say that this by itself is going to give you robust protection. Yeah, secondly. Well, just speak up.
Isn't this more of a semantic ambiguity of the if variable construct that basically says only if it's 0 does it do one thing versus any set of bits, and that leads to memory corruption vulnerabilities of any type?
Yes, the answer is yes. So the problem starts with the fact that the login program works in this way. But first of all, this is reality. You can just go to the Linux kernel and see that it is working this way. It would be quite trickier to write a login process that doesn't depend on a single bit decision. But the code itself was not built with this type of attacks in mind, right? Because if you don't have memory, prior to having memory encryption, you can just flip anything to anything. You can just completely bypass the whole logging process. So this type of attack was not in mind of whoever wrote this piece of code. So all these things become relevant when you have encryption on the memory. And then, oh yes, you can just go and try to rewrite all the code of the login process. But what about the rest of the things that are happening in the kernel? You cannot just, well, you can try to write all of the kernel code or anything in a way that would be better immune to such corruption.
Yes, EFI is written with macros, so there's basically a unique macro for success or failure of different types.
You can do this, but okay, one thing you cannot argue, this is the way that Linux is working today. Maybe it would be changed due to these things in the future. So, you can have this? Okay, we'll try this later. And okay, we'll be ready with this for the end of the next talk. So thank you very much.